So today we want to finish off our policy gradient, and then we want to implement a version of it. First in standard Python for the major parts, and then using PyTorch to make it run fast enough. It requires quite a high sample complexity, so we want to make sure that to be able to use the speed up that we get by using a GPU. And so this will be a reasonable target of trying to learn how to use PyTorch, which is a very popular library for implementing all sorts of machine learning, deep learning, reinforcement learning systems. Oh, the audio is not working? Oh. Then, testing. Oh, now it. Okay. Well, yeah, I need to disconnect, I think. Testing. Filters. Oh, testing. Oh, now it works. Okay. Weird. Okay. Yeah. So now audio should work too. So the motivation for the policy gradient algorithm is that so far we've dealt sort of with intermediate representations. We used either the value function or Q values in order to learn what actions to choose in a particular domain. Policy gradient is sort of saying, well, we're not clear whether this representation is actually a good one. So instead of having these intermediate representations, we should try and derive our policy directly. So the agent doesn't care about value functions or Q values. But what it does need is a policy. And we should think about what that policy would look like, the representation of that policy. Now, for a policy, the basic function is that given a state of the world, I have to return an action because I need to select an action, what I want the agent to do next. Now, since our domain is Markovian, that means I only need to know the current state, not how I got into this particular state. So the input to our policy will be just the current state. Got the history, and then I need to return an action, but I want to be able to represent more powerful domains, more powerful environments. So instead of just deterministically returning one action, I want to be able to somehow model the dynamics of the domain as well, deal with domains where I need to do some exploration. So I want to return policy. The representation of a policy should be the probability of choosing various actions. So an extension of just returning a single action associated with every policy, I have a probability distribution over action. So we're parameterizing this policy directly, and we expect the value of that policy given a set of parameters theta. So theta are all the things that we can change about our policy. So this particular representation allows us to select actions based on some probability distribution. Then the task is to determine the correct probability to choose. If our domain is not deterministic and I don't want to do any exploration, the domain is not probabilistic, then I would expect that the probability distribution will be 1 for one of the actions and 0 everywhere else. Which one simply would mean that for a particular state, we always pick the same action. Yeah?
What are the theta?
Thetas are the parameters of the policy. So the parameters of the policy could be different things. So if we have a discrete representation, right, then Theta represents the probabilities of choosing an action or state. So we would have a table of probabilities for each state. But that's not necessarily the only version. So if I represent my action selection as a Gaussian, then the theta would correspond to the mean and the variance of the Gaussian distribution that I'm modeling. And if I have like it's very popular now, here I would have a tabular representation. So I have a table of states. Every state has some cell, and then in that cell I have some information stored. S0, S1, S2, so on and so forth, right? So let's say I have 3 actions that I can execute, then A1, A2, A3, then here my policy will correspond of 3 numbers for each state. And that will correspond to say, okay, if this is 0.6, 0.1, 0.3, then that would correspond that if we're in state 2, we choose action A1 with 60% probability, A2 with 10% probability, and A3 with 30% probability. And it's supposed to be a probability, so I have to normalize it to 1. But, so in this case, theta, this would be theta I, right? The theta would be all of these numbers. That would be the representation of my model. But I can also have a state table. And I represent the policy. So here we have discrete actions, right? There's only 3 things I can do. I can do A1, A2, or A3, that's it. But in a robotics domain, I have an infinite number of actions. Right? So then, how do I generate a table of that? So in that case, we can represent it using a Gaussian, saying, okay, what is the action that you want to generate one, set the joint of your robot, draw it from a Gaussian distribution with mu1 and sigma 1. In this case, theta would be these numbers here. Because if I change theta, I change the behavior of the robot, the performance of the robot is going to change. Now, these representations, of course, are sort of limited because I still need to represent some unit of information for every state in my domain. But if I'm trying to play chess or Go or robotics, then I have an infinite state space. And if I play chess or Go, it's a finite state space, but it's extremely large. So I cannot really represent that in a table. Because either the table would have 10 to the 600 different entries, which is a huge, huge number, or it would be infinite, like for a robot. So in that case, our policy, what we usually do is we use a function approximator to approximate this state table. So we train something to feed in description of a state, and then it puts out these numbers, whatever my representation is. So a very popular way of doing this function approximation is using artificial neural networks or deep learning neural networks. So in that case, theta here will correspond to the weights of the network. Let's say I have certain input features. If I want to play chess, for example, then that could be the number of pieces that I have on the board. And this could be if I have a queen or not. And this could be if my opponent has a queen. Right? Any kind of description of the state, then that goes through some network architecture, and at the end, we produce an output, action 1, action 2, action 3, for example. So in that case, theta would correspond to the set of the weights here, because that would be the parameter of the model. If I change theta, I change the behavior of my agent. So there's different versions of this parameterization, depending on how we actually, how complex the domain is. So far, we've only dealt with very simple domains that we can represent as a table. But the algorithms that we have, they all can be extended to include a function approximator. So if your state space is enormously large, then instead of having a table, you train a network with some low-dimensional representation of what the information is that you want to provide to it, and then the output you want to train it to generate this action directly for policy gradient. Of course, we could also do the same thing with Q values and value functions. And in fact, one of the first algorithms to learn how to play complex games was Samuel's checker playing program. So he implemented a program that could play checkers, which is, I don't know if you know the game, but looks like this. Also called drafts. but you play it like that, and then you can jump over things. And so Samuels implemented a version of that in the 70s, and that state space is much smaller than chess, but it's way too large for a computer nowadays. And in 1970, it was way, way too large. So he used a linear regression in order to calculate a weighted sum. So instead of using a neural network like this, he would have, and that's sort of the simplest kind of function approximator you can implement. But the idea was that if you want to play checkers, then you can also talk to experts. You can ask them, or you can use your own knowledge, or you can read books. But you can figure out certain things about the game. And for checkers, certain things are certainly important. In particular, the number of kings. I think they're called kings or queens. The number of queens. And you can have more than one. That you have the number of opposing queens, the number of pieces, number of opposing pieces, the number of attacks, the number of your opponent attacks. So you can come up with a bunch of features that you can calculate very easily. So then Samuels assigned, in order to do his search, guided search, he wanted to have a function approximator. So instead of one way of doing the search would have been to say, oh, for state 0, I think whatever state 0 is had a quality of 12, if I calculate it. And this one has a quality of 15. And this one has a quality of 17. And this one is -3. Right? But way too many states. Billions and billions of them. So no way to do that. So he came up with these features. He thinks these features are important for determining whether you're in a winning position or in a losing position in checkers, chess, or whatever you have. And then he had implemented a function which gets these features and returns a valuation, and that particular function in his case was a weighted sum. So the number of white queens, 1, 2, and 2, times the number of opposing queens, plus W3 times the number of pieces that you have, plus W4 times the number of opponent pieces. So I forgot, he had like 6 to 10 of those. And they were symmetrical in the sense that if one thing was good for you, he also put the opponent one on there, because if it's good for you, then it's probably bad for you if the other guy has that. Right? Like, if it's good to have many queens, then it's probably not good if your opponent has many queens. So they were all sort of symmetrical. And then his model was, his theta were these weights. Because even though you can say a queen is good, And you can say that having an extra piece on the board is good too, if you want to win in checkers, right? Is one queen more important than one piece? No, because a queen can move a lot more powerfully. Like it can jump multiple times. The other one can just jump multiple times. Oh no, queens can go backwards. The other pieces can just go forward. So a queen is much more powerful, but is it worth 2 pieces, or 3 pieces, or 5 pieces, or 10 pieces? You don't really know. So he used regression to calculate these weights. But he could have also used a neural network or anything else, any other kind of supervised learning system. But it was very seminal work in the sense that not only did he implement the first game playing computer program for a complex game, but also he did it using machine learning. Because learning these weights is a machine learning problem. So theta can have many different forms. In our case, right now, we're just dealing with this the most simple representation here. So in that case, theta would correspond to the vector, the concatenation of all of these probabilities. And of course, what we then want to do is we want to change those probabilities. Right? And we want to change it in such a way that our performance improves. Okay. So policy gradient is an algorithm for making these changes to the parameters. And here it's very direct, but it can be more indirect through changing the weights on the network or anything like that. So these policy-based approaches, where we're dealing with the policy directly rather than through some intermediate representation, they have several advantages. In particular, usually they converge better. They work well in high-dimensional or continuous action spaces, where we have many, many different actions and highly dimensional state spaces. And we can represent probabilistic policies. I can now represent a policy that says 60% of the time do this, 10% of the time do this, 30% of the time do this. They also have some disadvantages. In particular, the gradient descent, the optimization function, now is quite complex. So there's a good chance that your optimizer will find a local maximum rather than a global one. So in that case, the simplest thing is to start from scratch and try new. Evaluating the policy can be quite time consuming because we need to sample the effects of all these parameters. And it's problematic if the variance of the policy is high. But that's in all learning tasks, in all learning problems. Right? If your variance is high, it's difficult to learn something or to draw a conclusion on it. Even if you have data, if your data has high variance, it's always much harder than if your data has a low variance. But it can sort of be amplified because evaluating the policy is time-consuming, inefficient. So if you then have high variance, you need to do many, many more policy evaluations. Because in a sense, what we're doing is saying, okay, we have some neural network, there's some weight here, that weight now is 1.3. If I change that to 1.4, will my agent work better or not? So that's hard to say. Then you need to run it over many different episodes to see if that now results in a better performance or not. If there's a high variance, then that means you need to run many, many more episodes. If there's no variance, you can just run, and you have good coverage, so that the parts of the environment that you're interested in are actually going to be visited, then you only need a few episodes. So last time we ended up with making a very small domain where we have a set of transitions and a set of rewards. And the transitions, the domain is represented as simply 4 states, state 0, 1, 2, 3, and 3 different actions that we can execute, and then these are just tables that say if I execute. So what this means is if I execute action 0 in state 1, I end up in state, action 0 in state 0, I end up in state 1. And if I execute action 1 in state 0, I end up in state 0. And if I execute action 0, 1, 2 in state 0, I end up in state 2. And here, if we execute A1 or A2, we end up in state 3. And if we execute A2, we end up in state 0. And these are the rewards. So if I'm in state 0 and I execute action 0, I get nothing. If I execute action 1, I have to pay $5. And if I execute action 2, it's also free. I don't have to pay anything. Also don't get a reward. So this would be the state transition graph and the rewards for our domain, for that particular domain. And let me make that a little bit smaller. So you can follow the state. So this is easier to see, right? So if I'm in state 0 and I execute action 0, I get reward 0 and up in state 1. And in state 1, if I execute action A1, then I get $100 UP, and I end up in state 3. State 3 is the terminal state. State 3 here, we go to state -1, which simply means terminate the episode. So then I implement two functions. Yeah. Do you think we should before? Okay. So I implement two functions, a successor function which simply says if I'm in state S and I execute action A, given the domain, and the domain now is completely specified by the transition table and the rewards table, then return the next state and the reward that you get. And then I can apply a policy. Now the policy in our case, in this case, would be just like this. And three actions. D0, A1, A2. So the whole policy can be defined by 12 numbers because I wanted to make it extremely small. Otherwise it will run too slowly. Training will take too long. Now you may say that in fact, it should be enough to just have 8 numbers, right? Because A0, A1, then since they have to add up to 1, this last number is known. Like if I know this is 0.1, 0.1, then this must be 0.8, no choice if I want to make it a probability distribution, right? So in theory, that's correct, but in practice, in that case, we will be treating A2 differently from A0 and A1, and it will not work so well. And in another problem that we would have is if I do some training and I start and I get 0.5 and 0.7, then what value do I give to A2? Because now it's already larger than 1, right? So then there's no way to turn that into a proper probability distribution. So we need to we treat all the 3 action parameters as sort of thetas in our model. Then I can change each one individually. And before we run the next step in our algorithm, I always normalize these numbers just to make sure. And that I can do based on anything. Even if this is 5,000, 500, 100, and 700, then I could 500, 600, 1300. So then this will be divided by 1300. This one divided by 1300. Now I have, like I just always have to divide it by the sum of the values that I have, right? Then I'm guaranteed to end up with another distribution between 0 and 1. and that sums up to one number. So my policy here, 12 numbers. That's all we need to know. Now we will try and develop the simplest kind of policy grading algorithm that we can think of. So apply policy then takes in a policy and a state, and then determines what the next action should be. So first we copy the values from our policy, and then I terminate them between 0 and 1. I clamp them to be between 0 and 1, and then normalize them, divide them by the sum. Because also I need to divide it by the sum, but I also need to make sure that all the values are positive. But this part here we don't actually need. I think. So we'll later on use logits here to make that a little bit more general, but for now this should be sufficient. Then we normalize it for this sum and change the value. Then I calculate the cumulative sum, which now will give me a number from 0 to 1. The sum at the end should be 1, right? And then I check where that random number fell in, and then I return that action. That's the policy, and the action is just returned as an integer. Now, this part here is in order to avoid rounding errors. Sometimes the rounding errors make it so that the sum or the cumulative sum will actually be 0.9999999999996. But then that's less than the 1 if I generate random number that is 0.999 higher than that. Then my algorithm wouldn't return the correct value. So I need to check if I actually selected a legal value, and if I didn't, then I just the last action. So the last action here will be chosen if I don't find one using the cumulatives. So then we need to come up with a way. What I want to do now is I want to optimize theta based on some objective function. So given a policy pi theta for state and action pairs, I want to find the best theta, the one that maximizes the reward that I collect. So I can evaluate the quality of this policy now, pi theta, depends a little bit on the domain that I'm dealing with, on the world that I'm dealing with. So for example, if I have, in our case, we start in state 0 and my uh, episode will end once I reach state 3. So then I can just evaluate the entire episode, and that would be then the value that I would get under policy pi theta for the initial state S1, which is the expected value under the policy pi theta for starting in state 1. But sometimes we don't have, so this kind of model matches things like playing checkers, because you start the game and then eventually the game will finish and you will either lose, win, or draw. So there is a definite break there. And then you go back to your start state. But other domains are continuous environments. So for example, yeah, I guess human life is a continuous environment, right? Sometimes probably all of you did something that certainly I have, where you made the wrong choice and now you have to pay the penalty. So you drove the car too fast, the police catch you, and you have to pay your fine. Then you would like to say, oh, maybe I can go back to the start state. No, that's not possible. So no way to go back in time. So in this kind of scenario, we can still assign a quality value to the how good that particular policy is by looking at the average value of the reward that we get over the last time, the last year or the last 5 years or something like that. Overall, the states that we're visiting, or you can also use the average reward per time step, because if your time horizons are very different for different actions, then they take different times, then that may not be, just using the average value may not be enough. Then you may have to decide the actual average reward for individual time steps for every minute. So it would be like, okay, now you can take the action to, yeah, I guess it's for you guys. Now you're in the master's program. Now you can think about, you can take the action of doing a PhD, right? But then for 5 years, you won't get any money, and then you can start collecting your reward for 4 years. Or if you go get a job now, then you can already start collecting every month. So in this case, the getting a PhD has a huge time horizon, whereas doing database development for 7-Eleven, you can do that every day and you can collect money every day. So in that case, you would want to look at the average reward per time step rather than just the reward for the particular action that you execute. So all kinds of versions, but there's some way that you can model the quality of your policy. And you have to be able to turn that into a numeric value, because otherwise you cannot optimize. So let's try and evaluate our policy. Now we're just dealing with the episode here. So I just want to calculate the expected value of starting in state, change it to S0, because in the example I use S0. So our start state is 0. Now initially, my policy, I don't know what actions I should use, right? I don't know the values of these numbers. So one reasonable thing to do in this case would be well, one reasonable thing to do would be to pick a random action. So if I don't know which action is good, then I just assign them all the same probability. So in this case, the policy, actually I only have 9 numbers because S3 has no actions going out of it. It's a terminal state. Now we have a terminal state. So now let's have a look and see how that policy does. So with the algorithms for 100 episodes, we start in state 0 and we calculate our rewards. We add our rewards. I don't add any discount factor at this point. And then I calculate the reward over time for this particular episode as well as the average of the rewards. And I plot them. Then we have this kind of domain. In our example, the reward is quite noisy. As you can see in the blue line, the amount of money that we collect while playing this game changes dramatically, but our average is sort of a lot less noisy. That's due to the fact that we're summing them. Yeah.
So we didn't update the policy, we just
No, right now I'm just evaluating the policy.
But the policy now is random.
The policy right now is random. Initially we set the policy to random, and now we're getting to how to improve the policy. So that is an optimization problem. And what I described is not the only way to do that. So there's many different algorithms for solving optimization problems. Our problem is we want to find theta such that it maximizes the objective function for this particular theta, the evaluation of our policy, the expected reward for our policy. Now, we will use gradient ascent in this case because I want to increase the value of my objective function. I don't want to decrease or minimize it. I want to maximize it. So we will use the gradient, but there are other approaches that don't use the gradient, like hill climbing, where I simply look what directions I can go, or simplex method, genetic algorithms, simulated annealing, and otherwise, but more common or Also very popular are gradient-based methods like gradient descent, conjugate gradient descent, quasi-Newton methods, things like that. These are more popular in this particular case because the gradient actually provides us with a powerful guide in order to speed up our search, in order to speed up our optimization. These algorithms here basically do more random guessing than the gradient descent based methods do, or gradient ascent based methods do. This shouldn't be gradient. Yes. So what we're trying to optimize is the gradient of the policy. So mathematically, this looks like this. This means gradient, right? Delta. Delta theta for policy pi theta for state action pairs. So that is a multivariate function because our policy, our theta, has more than one value, more than one parameter. So it's a multivariate derivative that we have to calculate. So the gradient is the generalization of the derivative of single value functions, multi-value function. So single value function, you calculate the derivative. On multi-value function, you calculate the partial derivative. And it's written with the delta symbol. So, okay. Now the simplest way to do that, and computationally it's not very efficient, but it does work, is to simply see, in order to calculate this derivative, because what we actually do is we change numbers here, right? So all I really need is a numerical approximation for this gradient. And then this I can do by calculating the derivative as a finite difference method. So I take current theta and I add a tiny little bit to it, and then I see how much the performance changes. So this is a dumb way of calculating the gradient, but it works and it's easy to understand. So the partial derivative of J for delta theta for individual k is I calculate the objective function for theta plus I change one of the values a little bit and mathematically represent that as epsilon multiplied by a unit vector. And the unit vector is like 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So it just changes one parameter at a time. So basically here, with our 9 numbers, I change the 9 numbers, each one separately, and then I evaluate, and then I see whether performance improved or decreased. So this means that for a parameterization with n values, with n parameters, I need to run n policy evaluations. Because I change each value a little bit once, the other ones stay constant. Now this works even if the policy, there's no, it's not directly differentiable. So I wrote a function to evaluate the policy. To evaluate it, we are running n number of episodes. We start in state start, and I pass in the policy and the successor function. And then I simply run that and return the average reward over those numbers of episodes. And I didn't implement a discount factor in this case. So the finite difference gradient descent then would be, given the policy and the successor function, I want to estimate the gradient of the 9 parameters that I have, but I organize them in this table so that it matches this, so it's easier to see when I print it out. And by how much do I want to change my values? Well, I'll just change it by 0.1. Actually, let's make that a little bit smaller. So first I calculate the actual current policy, and I run 100 episodes, start state 0, current policy, and this successor function. And then this prints out the average reward over those 100 episodes for this current policy. And now, then I change each one of them. And I can print out the gradient, I store the gradient, and then I can return it. So we start out with the random policy here first. And I pass in, I generate a successor function by providing a function successor, and I bind the transitions and the rewards. So that does pairing of the successor function, so that before I have to pass in 3 parameters, now I only have to pass in a single parameter for I have to pass in 2 parameters. Yes, state 0, action 1. So then let's see, but I don't want to print quite so much. So here the norm is the normalization of the gradient vector. So this simply means as I approach my optimal solution, if my optimization function is convex, then what I would expect to happen is sort of, it should look like this. Right? So as I run gradient ascent, eventually the changes are going to become smaller and smaller because the gradient will be less and less because I'm approaching a local maximum in the parameter space, which means that at the maximum, what should happen? If I do it like this for a single valued function, how do I know if I have a maximum or not?
You want to change the gradient descent constant zero.
Yeah. Yes. Without gradient descent, though, I mean, in high school, how do you find maximum and minimum values of your function? Huh? If I give you some, huh? Yeah, the derivative will be zero, right? So in order to find maximum or minimum, the derivative of a single valued function must be zero. Otherwise, it's not if it's differentiable. If it's a differentiable function, the minimum and the maximum, the derivative will be zero. And then you need to calculate the second derivative to figure out if it's a minimum or a maximum, or a saddle point. And because this would also be possible. So the gradient is the generalization of the derivative to multi-valued functions, which means that as we approach our best value, as we approach our maximum, the gradient is going to go towards zero. So here I simply check if the gradient is still large enough, I keep going. And once the gradient becomes too small, I stop. That's what the normalization is. So I calculate the let's just run it for 5 iterations. This just normalize. This just calculates the Euclidean norm of this 3 by 3 vector. So now, if you have a implementation like that, or if you have a problem like that, in fact, it's similar to lots of machine learning problems. Then now we're running gradient descent, and the rest of the code is actually nothing to debug really, because it's just floating point numbers, right? So we need to do gradient debugging to make sure that our function steps in the right direction. So here I want to specify the norm, but more importantly, I also want to evaluate the policy. So see if that's correct. Then I calculate the gradient, then I update my policy. So here the current policy at iteration 0, we have 33% everywhere, so random policy, and then we try and calculate the gradient by this finite difference method. So then we get the different values. So here I now change them by 0.05. So if I change the first, very high variation in that in that policy. And I think I need to run it for slightly more. And then I'm going to just run two. So here, random policy, if I evaluate it, I get a cost of 14. If I change the first value to 38, my expected, my quality for that particular policy increases to 21. So we get from 14 to 21. So that seems to be good. So let's see what that actually does. So if I go from stage 0 and I make this action more likely, then that will improve my policy. Not immediately, because I don't actually get any reward here. Right? Reward there is 0, but I end up with a state from which it's easier to reach state 3. If I execute A1, then I get a penalty, -5. And if I execute A2, I end up with, in this state here, state 2. So let's see if that is actually what we measure. So that's what we mean by gradient debugging, to make sure that your gradients are sort of stepping in the right direction. So far, when I evaluate my policy, I change this one here, I increase it, make it more likely, my quality goes up. If I increase this one, I have to pay $5, so my quality goes down. Because before I had 40 14, yes, now I have 5. And if I make this one more likely, then it also goes up. No, it goes down. That's because I'm more likely to end up in a scenario where my reward is going to, yeah, I'm more likely here, so I get less reward. I have a slimmer chance of getting the $10 as opposed to $100, and also a higher chance of having to pay the penalty here or paying the penalty there. And so we change each one of the change each one of the parameters of our theta and then evaluate. So 21, 5, 11, here I get 12, 9, 13, 13, 10, 16. So based on that, I can calculate my gradient. And the gradient basically says in order to increase my probability of getting a good reward, I have to increase the transition from state 0 using action 0, because that one, it increased from 14 to 21. And the other ones here, my value goes down. So I recorded, all of these are bad. Here, all of them are bad. Here, these are all bad. This one is good. So it says in state 3, in state 2, we should execute action 3. We would like to prefer us to do that. So in state 2, we should do action 2, which is go back to here, because that will allow us, we only have to pay $1, and then from here, I can go to there without having to pay anything. So that's cheaper than paying $10 and then ending up in this particular state. So then I changed my policy, and if any of the values goes negative, I push them all up to make sure that they're all positive. And then I can normalize them. The problem is I have to figure out a way, because I simply add and subtract values, right? So the simple thing is if I have -5, 7, and 9, and I want to normalize it, then I make this one 0, 12, and 14. Then I calculate the length of this gradient vector to see how much change I made. If that change is still large, then I keep iterating. So in this case, I want to run two policies. So after we make the change, we end up with this policy here. And I should have normalized. Might as well normalize it here. Well, let's say S is equal to CS divided by the sum of policies. So Bradian now is totally different because we made the high variance, so we need to run it multiple times. And that's why we also have a learning rate here, alpha, which is pretty small. Okay, let me try and stabilize. Okay, then let's try and run another couple of episodes. So our average policy has a quality of 14. And then next one, we obviously made a bad move because our quality is minus 52. No, that's the problem. Now let's see what it looks like. So random policy, we evaluated to 13. We get 15, 13, 11, 11, 19, 13, 13. Then I calculate the gradient and the changes, and then update my policy. So in the next round, instead of 0.3, 0.3, 0.3, I end up with something like that, 0.6 and 0.36. And actually these ones are pretty much, if you look at this value here, then after the first round of our gradient descent, gradient ascent, it now says basically this one is much preferable to this one and that one. And what does our state machine say? So state 0, A0 we get to here. So this is a good state because I can get $100 reaching state 3. So that would be our optimal policy. Here I have to pay $5, so that's no good here. I don't have to pay anything, but the state that I'm in now, I either get $10 or I have to pay $10 or $1. So state 2 is also not desirable. So it's making the right choice now, and now these are sort of propagating. Here it doesn't want to do this. State 1, it wants to do action 1. So what will that give us? State 1, yes, definitely do action 1 because you get $100. state 2, I think state 2, the best action to do was to go back to state 0, which should be action 0. Let's check. Oh, it prefers this one. I guess because we can still get $100 even though we have to pay $10. So then our evaluation goes up to 94 and our norm 137. This is the gradient here. Now, yeah, the gradient starts to slow down after 10 iterations. Then we can look at our current quality measurement J. So we start with 13, then we go 94.9, 92, 93, 94.3, 95, 96, 96, 96. So we can plot the performance of our algorithm. Now I don't think I need to iterate it quite so high. Yeah.
Should the norm of gradient become smaller?
Once I think my jumps are a little bit too big, so if your optimization function looks like that, and you jump from here to there, then your gradient doesn't really become smaller. So in that case, I would have to decrease what would I have to change?
Learning rate.
Yeah, the learning rate. Then I can slow down the learning rate, then I'm more likely to end up here. So let's do 500. Actually, I just leave it at 5,000 here. And I just want to show the actual J, how it performs. Changes. So that means I need to evaluate the current policy, 1,000 steps. So that's that. So I want to be able to turn on and off the printing. And then here, change the learn rate a little bit. 100 iterations, no printing. Oh, I wanted to. Okay, so here it just terminated after next episode because the gradient was small enough here for the normalized value. Or, I don't know. Number of iterations. And then here's the performance of our gradient descent. The more think that's, I want to use a smaller epsilon. I just want to use this. So plotting this, we can see that our objective function increases, keeps increasing. I haven't tuned it yet. It's hard to find out exactly what learning rate I need for it to run fast enough so that we don't have to wait too long and still not jump over any peaks in the any minimas in the optimization function. But more importantly, let's just have a look at the output. So here, after our gradient descent, our objective function jumps up and then sort of starts increasing slowly, or keeps increasing slowly. But now the variance within the policy evaluation is a problem. But if we look at the policy that it learned, does it make sense? Well, for S0, let me write down the numbers we have. 0.84, 0.1, and 0.005, and then 0.5, 0.5, and 0.3, 0.6. Now, given this particular domain, if we had learned the policy correctly, then these numbers should be 1 and 0, 0, because a deterministic policy would work for this particular domain. So in state 0 now, it's very keen on doing action 0, which is correct. That leaves us there. State 1, it wants to do action 2 or action 3. So action 0 and 1. Because there's no discount factor, so it's also happy to go back to state 0. Now, that if I added a discount factor, then that would be, it should then prefer to do A1 instead of A2. But it doesn't do A0. It doesn't like to do A0. 0% probability of doing that. And from state 2, it says to A2, which is the cheapest way to get out of this state here and still have a chance of collecting this reward of 100. So the policy makes sense. Actually see if I just run that and increase another, because this is easier than I thought. So And you can play around with the parameters and see the different changes in the performance. Now I think we have more variation, more variance. Ah, no, I didn't run this. I wanted to run this. Okay. Yeah, so now with the higher learning rate, we also have to sort of expect higher variance in our learning. We get a higher value up to 98 now, but also higher variance. And let us run it one more time with I want to make it bigger. And then 3. Oh, I can set it really small, then the changes will be much smaller. So the impact on the quality of the policy will be much reduced. Or should be. Of course, it could all be. It is all random, so there's different results are possible. you're just unlucky. I don't know what happened to my figures. That's weird. How come? I think that's something to do with because it just drew the figure just before. Now, here. Okay, so now much less fluctuation in our performance. So now I just need to take 5 minutes to go to the washroom quickly, then I'll be back. Then we'll look at the analytical solution for the gradient descent algorithm. So just give me a couple. So computationally, it's not very efficient. It's easy to understand what we just did in a sense, right? Because we took our parameters theta and we added a little bit in order to estimate if I, basically in order to estimate if I add a little bit to this parameter, is it getting better or worse, right? And how much better or worse will it get? But we have to evaluate the policy then quite extensively. So it's not a very efficient way of dealing with this particular problem. Analytical solutions usually converge faster and more directly. Now, to implement that, we can introduce the idea of likelihood ratios. And the basic um, tenets of it, or the idea is that we need to calculate the gradient with respect to theta of our policy by theta for state action pairs. Now, that's equal to the value of the policy multiplied by the gradient divided by the policy. So I can multiply that out. That would be the policy multiplied by the gradient of the log of the probabilities of this particular policy. So this then, the gradient of the log becomes the scoring function that I want to use, or it's called the score function. And oops, the basic add one more here. This is based on the fact that what's the derivative of the log of x? That's correct. So over x, right? So then so that means that d of x radian will be equal to x log x. By reformulating it. Then this is the same trick here. So one algorithm that uses that, or one common implementation is the reinforce algorithm. It runs the steps that we just implemented, except here we calculate the gradient of the log of the probabilities for our transitions from state and actions at time t, and then multiply. So that is a very popular algorithm of and implementation of the policy gradient method. Calculating an analytical solution to for the policy gradient. So one thing that you will read up, or that is used a lot in reinforcement learning algorithms in general, and machine learning algorithms as well, but the notion of entropy and entropy regularization is important. Now, before, we already talked about the exploration versus exploitation trade-off. When we discussed the one-arm, k-arm bandit problem. So what does this actually refer to? What do we mean by exploration versus exploitation trade-off?
We want to explore the environment. We can have more information on the environment and end up with a better result. But it costs time to or more answers to explore.
Yeah. So we want to avoid premature convergence on non-optimal or worse or bad solutions that we may just end up with. So for example, if I look at my state and my small reinforcement learning problem here, then let's say randomly I pick actions and I end up doing action, I go from state 0 to state 0, then I do A1, then I do A2, and then I do A1 from state 2. In that case, my reward for that particular episode would be I have to pay $5, then I don't get any reward, then I get $10. So my reward is plus 5. If I have not tried any of the other states, right, then my estimate for this particular action sequence would be pretty good because I got at least $5. However, if I now just keep doing this over and over again, then I miss out on the $100 I could get if I move to stage 1. So, how do we solve that trade-off? How do we usually deal with this particular problem? For the k-arm bandit problem and TD lambda, for example, we implement epsilon greedy policy. That's correct. Where epsilon greedy simply means that we take the best action, but with probability epsilon we take a random action. And then we decay that epsilon over time. So initially I'm willing to make more random moves, but as I do more and more exploration of the domain, I'm less and less likely to allow random movements in my agent. And that works in practice quite well. In the K-on Bandit, it actually gives us a performance that is pretty close to optimal. There's of course other policies that you could implement. Another common one would be to have a policy that says, okay, you must try every action at least 10 times. So that forces more exploration than epsilon greedy on average, because now you're guaranteed to have tried every action, but whether this is reasonable or not depends on your domain. If it's a vast domain with millions of actions, then you cannot try all of them n times, or k times, or whatever. So that wouldn't be reasonable. Also, to use that approach, not only do you have to explore then really every action, so the exploration is very good, like you're actually guaranteed to have visited every part of the state space that you can reach at least n times, right? Because if you have tried every action, then you get to a successive state, so as long as it's tree-like, you would end up with exploring the entire domain, which is very good, so exploration is very good. But the cost is maybe high in the number of actions that you need to execute, and also memory-wise, space-wise, it's not such a good strategy, because you need to keep track of how often have I tried state action 0 in state 1, and how often have I tried action 212 in state 1019. So to keep all these counters, you add a lot of extra memory to your reinforcement learning. Epsilon greedy is much easier, right? You just need a single number, one floating point number. And it does a reasonably good job exploring the environment as well. If you come up with a sort of simple linear decay on your epsilon parameter, then that works quite well in lots of domains. And sometimes you need to tune it. Sometimes you need to be more careful about that. Entropy regularization is a different approach to that particular problem. So what is entropy? And how can we apply it to our policy? So entropy is
the probability times the load or probability of that particular of state.
well, the formula for it will be sum over all the actions of, and I can take the negative sum out. So this would be the formula for calculating entropy for a, let's say, a system that has, with probability P of A, select certain action in our policy. But more generally, entropy measures the amount of the what? Disorder, yes. Either in a physical sense, it would be the amount of disorder, or looking at it the other way, it would be the amount of information in a message or a sequence in a system. So if I calculate this, P of A and log P of A, if we have a system that sends 3 types of messages, P0, and it sends P0 with probability 0.25, P1 with probability, yeah, well, I'll just do 2 and then change it, 0.75. Then the entropy will be the minimum number of bits to send a message, or yeah. Now, if I only have 2 messages, then the message occurs with probability x from 0 to 1. And we have the negative sign there because the logarithm of a number less than 1 is negative, right? So, but I want to measure it as a positive number of bits. So if I only have 2 types of messages, then if I have probability of x for one message, then the other one must be 1 minus x, right? 1 and 10 divided by, sure. Then you get this curve, which is, I'm sure you've seen before, and maximizes on 0.5 here, but if either one side or the other side of the message is close to 0, right, then it contains very little information. But we can extend this to multiple types of messages. So in our case, 0.25 about here, then every element or every message can be encoded in half a bit. It's log 2, not the natural logarithm. So I can log 2. Oh yeah, I can specify. And then if it's 50%, then I don't know what I can send. In this case, I will have to send 1 bit. If there's a 50% chance that it can be on or off message, then I have to send 1 bit of information. No other way to do that cheaper. If you only have 0.2, then you can send fewer bits. You can group messages together and use a different encoding where you only need 0.6 odd percent. 0.6 bits per message. Now this is the theoretical minimum. There's no possible encoding scheme you can come up with that requires less bits per message. It's impossible to do that. We know that because of the measurement of the entropy. And then we can apply the same thing to our reinforcement learner. So what would I use for the entropy then? Well, I can apply an entropy bonus. So the entropy of a policy, since my policy is all probability values, I can simply calculate that as the sum of the probabilities multiplied by the log 2 of the probabilities, the negative, sum them all up, and then I get an entropy value of a particular policy. And if my policy is extreme, like if I'm close to 1 or to 0, for any of the probabilities, that means that the policy is sort of very much determined now. Right? If I think about this curve here, instead of sending messages, if I think about this curve for selecting actions, and I'm in this part of the curve, or in this part of the curve, I do very little exploration. Because here, I will have a probability of 1 of picking action 0. And here I have a probability of 0 of picking action 1, which means I have a probability of 1 of picking action 1. Right? So both of those cases, the agent is going to pick the same action all the time. So the entropy for this particular policy would be low. And we can then say that this particular policy will not do a good job exploring the environment. So the entropy of policy pi with parameters theta Some theta, okay, above pi. And now what we can do is add entropy bonus to, so that means I prefer policies that are good, but also still have room for exploration. So instead of when we looked at our objective function here, what we were trying to optimize was this one version of this. Right? This was our objective function. For this particular example, I was optimizing this one. Now I change it, instead of just j of s0 of theta, I return the quality will be j of s0 of theta plus k times the entropy bonus of policy theta, or policy phi theta. In that way, we can force the algorithm, similarly to epsilon greedy, we can force the algorithm to continue to do experimentation, exploration. And that's a practical improvement to reinforcement. Otherwise, especially in policy gradient, there's a high chance that you end up prematurely converging on a non-optimal solution, depending on the domain that you're dealing with. But that happens quite often. So your quality measurement, your objective function becomes the performance of your policy plus some factor of the entropy, and then that can then change how much exploration is important to your particular policy. That's a common way of improving the policy gradient algorithm. It's a common extension to the standard policy gradient algorithm to also include a term that prefers high entropy policies. Another way of thinking about it is that if there are multiple ways through your domain, right? If there's two possible ways to go from state 0 to state 22, then if you happen to pick one, let's say action 1, but action 2 will do the same job, then you want to maintain both of those as possibilities. If you don't have entropy regularization, your algorithm is going to converge on one of them. Or it may converge on one. Okay, good. Then that's it for today. Next week, like I said, we will do PyTorch. I would like to introduce you to PyTorch. If you have never used PyTorch before, then it's an extremely popular library for doing all kinds of machine learning using GPUs. It's actually developed by Facebook and Jan LeCun. So it's in the machine learning space just as important as Matplotlib is in scientific computing. It's actually a pretty neat library. So we'll try and implement policy gradient using PyTorch next class. And you sort of need to do that if you want to have more, like you can implement it like this for small domains, like 4 states, but if you want to do something a bit more interesting, then you are better off to do a proper implementation using GPUs so that you can run larger batch sizes. Computationally, the policy gradient is requires more training than PD lambda on a grid growth domain, for example. Okay, good. Then did you fill out that the sheet you're supposed to fill out for attending class? No? Is there anything here? Because they gave me one in the morning, so I assumed there would be one in the afternoon class too. Yep. It's in video. So yes. And then we also have to take away the camera.